Guys, today is a very exciting day. We're talking about hash tables today. Hash tables are one of my favorite, if not my most favorite, data structure of all time. Between hash tables and vectors, that makes up the vast majority of everything that I need from the data structure side of things, 90+% of the time. Okay, so a hash table. Here's hash tables and why they're cool in a nutshell. Order one, insert, search, and delete. Assuming everything works well. There's asterisks on those. But order one, insert, search, and delete. You can insert something in constant time, search something in constant time, delete something in constant time, and that seems impossible. How do you add something to a database and retrieve it so quickly? So to help you build some intuition as to understanding how we could exactly do that, imagine that we're trying to store social security numbers. Okay, so we're going to make a set that holds social security numbers of people that have, checked in at this hospital or something. So what we could do is if you have an unsigned 32-bit integer, there's like 4.2 billion possible numbers and change, right? And so what we could do is just make a bit field, a bunch of zeros and ones. These are slots. And if if you want to see if a social security number 420 is in the system, you just go to slot 420 and you're like, oh, that one's false. Nope, never met person 420 before in my life. But if that slot was true, then yeah, they're checked into the hospital right now. You guys see how easy that is? So if you want to insert somebody, so like if you want to check somebody into the hospital, you're like, all right, person 6900 is now checked in. You go to slot 6900, right? And you make it true. And then if you want to erase from the hash table, you just set it to false. Person 6900 is now not in the hospital. And if you want to search, is the person in the hospital? You just look it up. It's easy. Array, square bracket, 6900. Yep. Are they in there? True or false? That's it. Done. Lecture's over. You might have a question here. Well, isn't an array with 4.2 billion, isn't that kind of big? And back in the day, it would have been, right? Like it would have been like we used to joke about it. Like you just make a hash table, every single possible integer. But nowadays, 4.2 billion bits is how many bytes? There's 8 bits in a byte. So if you have 4.2 billion bits, how many bytes is this? How many bytes of RAM would it be to hold this entire ridiculous thing in memory? You can hold a true or false value for every single possible integer. How much RAM is that, people? Come on. 4.2 billion divided by 8. Megabyte, 5 megabytes? Nah, it's going to be close 500 megs, right? Ish. Change. So it's about half a gig. It's not that bad. It's still more than I want to spend, but it's not that bad. Does this make sense to you guys? Like you just make an array of size 4.2 billion, and if you want to insert something, you just go to the bucket, which is what we call a array slot. You go to the bucket, if you want to check person 7, social security number 7 into the hospital, you go to bucket 7, you set it to true. That's it. You guys understand? Pretty easy, right? Pretty straightforward. If only there was a way that didn't require half a gig of RAM. All right, so maybe there is. So let's draw. Let's see here. Let's do a shape. Okay, so we're gonna make a shape here, and we're just gonna draw some lines. Give me some lines. 2, 3, 4, 5, 6, 7, 8, 9. The buckets are getting progressively bigger as we go to the right. Slot 0, slot 1, slot 2, slot 3, slot 4, 5, 6, 7, 8, and 9. So we've got a size here of 10. We've got 10 elements in this hash table. This is a much smaller hash table. This one is going to hold integers in it, so 4 bytes per integer times 10. This is 40 bytes. The B here is not a billion this time. it's literally 40 bytes. So instead of 500 megs of RAM, it's 40 bytes for this hash table here. Can't hold many numbers, but it'll help demonstrate the point. So everybody, give me some social security numbers of people to check into the hospital. We're gonna check people in, check people out, search to see if they're in the hospital, and we're gonna do all this based on their social, because socials are unique to each person. That's why they exist still. Okay, let's insert 1. So we're gonna put the number 1 into slot 1. 7. We're gonna insert the number 7 into slot 7. So far, so good. But what if somebody has a social security number bigger than 9, which all of them are. So we got Sabrina's 6843592. That's going to go into slot 2. How do I know it's going to go into slot 2? It's because the value modulus the size is the bucket. And anytime you modulus something by 10, you just get the last digit. 45 modulus 10 is 5. 63 modulus 10 is 3. 111 modulus 10 is 1. Okay. So Sabrina's 6843592. 2 is the last digit. So it's going to be a 6843592. Great. Gunnar Lamar's got a 20 in there. 20 modulus 10 is 0. Because 10 divides into 20 2 times, the remainder of 0. Cool. So far, so good. Now there's an obvious problem here, which is we're going to get what's called a collision. Our hash table is so small, as we keep inserting numbers into it, we're going to get a collision. And how we handle a collision really, really depends upon the type of hashing we're doing. So if you have no collisions, basically all hash tables work the same. Basically. But when you get a collision, how you handle that is where all of the intelligence of the hash table is. So today, we're going to be talking about 2 different types of hash tables that differ only in terms of how they handle a collision. The first is called linear probing. The second one is called chaining. We're going to do chaining with BSTs. Okay. So we've got Jose Santiago wanting to insert 111111111. That's my social. This is going up on YouTube, so yeah. That's my social. All ones. Okay, so that should be trying to go into here. You guys see that? 1111111. It's supposed to go into bucket 1. Now, if we're doing linear probing, the way that it works is if a bucket is full, we check the next bucket to the right. So that bucket's full, so we check the one to the right. That one's full, so we check the next one to the right. That one's open, so we insert 111, 11, 1111 into bucket 3 instead. And so I think you can see an issue here, right? Which is as the hash table gets full, if there's only like one slot left, this beautiful order 1 time turns into order n. As if it's empty, as it fills up, it goes from being really, really fast to terrible. Okay? So empty hash tables have great performance. A full hash table with linear probing has order n performance for insert, search, and delete, which is terrible. Okay? So there's different tricks people use. The standard library, when the hash table gets 80 or 90% full, something like that, it doubles in size and it rehashes everything. So it's kind of like with a vector. When a vector fills up, it doubles in size, copies all the elements over. So a hash table that fills up, a professionally made one, will double in size as well. But for this, I'm not gonna make it any bigger. We're just gonna observe the destruction of humanity. So what if we want to do a search now? What if we search for 111111111 now? It's the exact same algorithm. We take the value 1111111, modulus it by 10, and we check here. Is it empty? No. Is it the right answer? No. So then we have to go to the next one. Is it empty? No. Is it the right answer? No. We have to go to the right. Is it empty? No. Is it the right answer? Yes. Return true. But if that wasn't it, then we'd have to go to the right again. Is it empty? Yes. Return false. So when you do linear probing, if you're searching for something and it's not in there, you have to keep going to the right, going to the right, go to the right, go to the right, until you find an empty bucket, and then you return false at that point. So that's searching. What about deleting? Okay, deleting is always the hardest part of a hash table. Let's say we delete the number 1. And now this spot's blank again. Now we've got a problem, right? Because if we say, hey, is 111111111 in here, we hash to bucket 1, it's open, we return false, and that's wrong because 111 is actually in there, right? So what you got to do is there's a couple different approaches you can take to it. You can do what's called a lazy delete, where you just mark it as deleted, and then if you do a search, then it'll just keep checking to the right. That's one approach you can take. Another approach you can take is to rehash everybody to the right until you find an open spot. So you'd rehash this guy. You would go back into 2 because his last name's 2. Last digit's 2. But then this guy would get moved into here. 1, 1, 1, 1, 1. And then everything is right with the universe. So depending on whether you want to do more work when you do a delete or not, depends on the algorithm you use to delete it. So there's these things called lazy deletes, and then there's all sorts of other schemes to like steal things and put them in the bucket and stuff like that. Okay, so that's linear probing. You guys understand? Insert, search, delete. It's very fast when the hash table is empty. When the hash table is full, the performance crawls to a halt because, you know, if there's only, like, let's say all of these have numbers in it, right? Except for 8. And you insert 1111111. You come in here, it's old. Okay, let's put a 0 there. So we come in here, it's full. Go to the next one. It's full. Go to the next one. 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 You see how this order 1 turns into an order n. And then we finally can insert 111. Okay. So when you got only 1 slot left, yeah, you're going to be probably going through, you know, the whole thing, right? If you do a search and it's not in there, you're basically going to run through, you know, n elements checking to see if you got a hit. So the kind of the takeaway point from this is that if you want your hash tables to go faster, you make them bigger. You guys understand? The bigger the hash table is, the less likely that 2 numbers are going to hit the same spot. And so just throw RAM at the problem. This is the big think about hash tables, is that the more RAM you throw at the problem, the faster your algorithm goes, the faster your program goes. And for a lot of applications, it's not even that much. Like if you're keeping track of like 1 million people's social security numbers, you know, you could probably do so in, I don't know, 2 million records, 2 million integers, there's 8 megs of RAM. 8 megs of RAM. Who cares about 8 megs of RAM? Let's throw 100 megs at it. Let's make sure it's fast. You know, let's go wild with 100 megs. You know, I got 64 gigs on my system here because I do Unreal Engine development. You know, like 8 gigs is like whatever. You know what I mean? Like, let's go crazy. Let's make it 24 megs of RAM. You know what I mean? It's like, it's like for a lot of like real life applications, like, you know, I'm not talking about like Google and like they're like giga scale, like, you know, we need a hash table containing every Gmail address ever. No, nothing like that. Nothing like that. But for like, you know, how many patients are checked in at a hospital at a time? You know, like 1,000, 2,000? I don't know, somewhere like that. You know, you can have a hash table holding the social of every person held at our big hotel hospital. It's an overnight stay, but not the kind of one. You know, if there's 2,000 people at Community downtown, you know, maybe you make the hash table of size 10,000. So there's, you know, very little chance of a collision. 10,000 integers is, you know, 40K of RAM. 40K of RAM. It's nothing, right? So at the scale that a lot of people operate at, like, you could just throw more RAM in it. Like, oh, let's go crazy. Let's make it 80K. Let's make it a megabyte. Whoa. You know, a megabyte to hold 2,000 integers? What luxury is this? You know, and back in the 70s, that's what they would have said. But nowadays, it's like, RAM's cheap, man. I'll tell you. So do you guys understand? That's the trade-off. So you can throw more RAM at a problem to get your program to go faster. When you start running out of RAM, the hash table slows down and becomes like a worse version of a vector. You guys understand that? It's gonna be on the quiz for today, so hope you understand it. Yeah, and so it's a different world when you're talking about like Facebook, Google, Twitter, like the kinds of problems they have to solve. Like, how do you have a hash table that's shared among multiple servers? These things called distributed hash tables. Like it gets complicated, but like I work with school districts, and the biggest school district I worked with, I don't know. I guess I worked with a consortium of school districts. Maybe 1 million kids between all the different school districts in this consortium, and that's still probably no, it's not even 1 million. It's not even 1 million. Maybe the highest possible 200,000 people, and that's the biggest project that I worked on. Was with 200,000 records probably per year. So over 5 years, yeah, maybe 1 million, right? That's and that's like what? It's like nothing. 4 megs of RAM, 10 megs of RAM. Not a big deal. Okay. Now, what's the difference between linear probing and chaining with BSTs? What's this guy here? Well, chaining with BSTs avoids the linear probing issue entirely, and it has a better worst case time. So instead of order n, the worst case time is going to be order log n. Okay, and let me make that a little bit bigger so it's a little bit more readable. So as your chaining with BST thing gets overloaded, it degenerates into just order log n performance, and order log n performance is good, right? It's actually really fast. Like a log n algorithm is actually really fast. Hash tables are the only thing faster than a binary tree. Binary trees are pretty fast. Hash tables, like if you have 1 million elements, binary tree will take 20 operations. A hash table will take 1. So hash table is 20 times faster. So it's noticeable. But log n is actually really fast as it is. Okay. So now we're going to do this same insertion. We got 10 buckets here, and I want you guys to start tossing numbers at me again. So give me some numbers on chat, and I'm going to insert them in here using chaining with BSTs, and you're going to see the difference between this and linear probing real fast. Hopefully, if there's a collision, if everybody gives me like a different bucket, then you won't see anything. Okay, so we got -1. All right, so -1 is an interesting question. -1 would actually go here, right? Because you're at slot 0, 1 to the left is -1 is 9. Okay. 69. All right, so 69 would go here. 3, 7, 5, 69, 84. Okay, 3, 7, 5. I'm just gonna write 3, 7, 5, 4. Yep. 72 for Gunnar Lamar. 72 comes in here. Luke Olson, 42. Look at this. It's a binary tree, people. We have made an array of binary trees. Yes, we have. James Hernandez, 79. So 79 will come here. Now, these are actually balanced binary trees, so this thing would probably do a rotation. And we would end up with 69 as the root instead, with 79 to the right, and -1 to the left. If your tree becomes unbalanced, you can do a rotation and fix the balance problems. Again, how you do that is a junior level topic. I'm not going to go into it now, but just be aware, if you have a balanced binary search tree, then the worst possible scenario you have is that everybody hashes to the same bucket. You insert 1, 11, 21, 31, 41, 51, 61, and all of them hit the same bucket. Oh no, you're a binary tree now. Not that bad. It's not that bad. You've made 10 binary trees, but all these other binary trees are just null pointers. I don't know. Yeah, it's a little bit of RAM. It's not the end of the world. Okay, 42. Then we got 79, and then we got 21. So 21 would go into here. Okay, you guys understand? So we have made a forest of trees. We've made a forest of trees. Make sense? We have made an array of binary search trees. And I can show you guys how to code this real fast, making a hash table is actually pretty easy. All things considered. Now there's more complicated hash tables that are a little bit more involved, but I'll show you. Let me get my tablet put down here. And just code something from scratch. We'll hash table action here. I'm going to include set. And it's enough. Class hashy. And let's do probing class prober. How about that? Okay. So this one will have an integer. Now, let's do this properly. Let's teach you guys something new. So we're going to do a template, and it's going to be templated based on class T and integer size. Probably should be a size type. Okay, and so what we're going to do is we're going to make an array. Like before, we were just making an array of like size 10 or something like that, right? In my example before. But instead of it being integers, we can work with any type. So we're going to make it work with type key. And the array is going to be of size. Do you guys know what the curly boys do there? What do the curly boys do? Sets the whole array to 0. Now, very good, Luke. Is this stack allocated or heap allocated? Do you see a new there, Stevie? If you don't see a new, it is going to be heap allocated. Now, sometimes that's not sufficient because if you make a vector, vectors under the hood call new. But this is just a C-style array. C-style arrays are, unless you see new, they're stack allocated. So if we make this size big enough, we're going to crash. So, the more proper thing would be to new it, which maybe I'll refactor it in a second. But for now, let's just get this thing working. Okay, so now we're going to say 0 means, 0 or empty, whatever it means the slot is empty, which is not the right way of doing it also. Sometimes you might want to insert the number 0. But if we're doing social, 0 is not a possible social security number. So if we have a 0 in our hash table, that just means there's nothing there. Okay, so we need a constructor. Nah, constructor is fine. If we're gonna change this to be heap allocated, we can mess that in a bit. But for now, what are the 3 main commands that we always do with the data structure? Not always, but what are the 3 big important operations we do on data structures, like linked lists, vectors, binary trees? What do we call them? There's insert. All right. There is search and there is delete. So search will return a boolean, and it'll be a const t reference. Needle const method, and then we will have a void. We can't call it delete, right? Delete is a reserved keyword. Can't call it that. So the standard is to call it delete like that, right? That's the standard way. No. So we have insert, search, and yeet, right? No? Yeah. Perhaps erase. Yeah, that's the standard. Very good, Luke. And then I don't know. Let's just call it X. I can't come up with good variable names here. I'm sorry. X. Okay. Yeah, there we go. All right, so here are 3 functions. So for insert, but we're doing linear probing right now. Okay, this is the probing one. So if we're inserting, okay. So first thing we do is we need to find what slot we go to. So we can call this size t hash t x. And we will return x modulus size. Okay, so size is the size of the underlying hash table. And so you've probably never seen this before, where you can actually pass in an integer. Size t is just an unsigned 64-bit integer, as well as a type. You guys have seen this, where you pass in a type, so we can have a linked list of integers, a linked list of floats, a linked list of doubles, whatever. This, though, you can actually pass in anything as a temporal parameter, basically. And so that is the size of the underlying array that we're using. Professionally done hash tables, again, when they fill up, they're going to double their size and rehash everything. We ain't doing any of that right now. We're just making a super basic hash table. So we're going to make a prober. It's going to hold integers, and the size is going to be 10, and we're going to call this guy hash table. Hash. How about hash Ketchum? No? No. Gotta catch them all? No. Got nothing. Hazelton, what do you think? Is that a good name? Hash Ketchum? Yeah. Dead. It works, I guess. Hardest thing. Good name. Okay, we got a beautiful from Hazelton. Great. Okay, cool. So hash Ketchum. We're going to say hash Ketchum dot insert. We'll insert 10. 20. 42. 60. And 50. Okay. All right. And then we will check to see if hash Ketchum dot contains search the official. See, I never know what to name something until I actually try using it. Then whatever comes out of my fingers, like, oh, that's the name. Contains. There we go. Okay. Contains. If hash Ketchum contains 10, then we will see out 10 is in hash Ketchum. Else 10 is not in hash Ketchum. And then we can do the same for a number not in there, like 100. And then we can do like a delete. So we can do like a delete. Hash Ketchum dot erase. Pull the number 10 out. And then we can do these things again. Okay, so we haven't written the code yet, but we're just kind of getting the driver ready, right? So this is a little driver code in main. It's just going to put some data in, test it, pull some data out, test it. You guys understand? It's a stub and driver development, right? Main right now isn't even a main of anything. Like there's no interface. It just, all it does is it just puts data into a hash table, tests it, make sure everything's working right, and that's it. Like it's not like an interactive program in any way, but it's a great way of doing development. So Boolean contains, we could probably have this like return false just to get it to shut up about the warning. Okay, so to insert. So the slot that it's going to go to can be determined by this function. It's called a hash function. So if we have the number 42 for x, it's going to modulus by 10, and it's going to tell us go to slot 2. So for insert, worst case, we have to check every slot in the thing. So the first slot we have to check though is hash x. For int I equals 0, I is less than size I plus plus. So worst case scenario, we have to check every bucket. But ideally, if our hash table is big enough, the very first spot we go to is going to be empty, and then we're done. So worst case, it's order n. best case, order 1. And the more order 1 you get, the bigger the hash table is. All right, what is your problem? It's a yes, fine. We're all unsigned integers now. Cool. Okay, so if the spot that we found is open, then congratulations, that's our spot. We insert into it. So if our square bracket slot is empty, then, and by the way, this is not going to work for every type of T. We need something better than this. Like I said, the default value, showing that something's empty is actually a little bit more work. You usually have like a bit field or a status thing that says for each bucket whether it's filled or deleted or empty. But we're just doing a very basic thing. This code's only going to probably work with integers. Yeah, probably. And so this little class T thing here is probably a lie, but yeah, whatever. Anyhow, we're just trying to get this going so you can see how this works. So if the bucket that you're hashing to is open, well, if we tried inserting 66, suit order 66, the value here is 0. And so all we do is we just set the value array slot equals x, and we're done. Return. So ideally, the very first time we go there, the slot's open, we put the value of 66 into slot 6, and we get out. But if not, then we need to move 1 to the right. So slot is equal to slot plus 1 modulus size. So if the first slot is taken, then we move 1 slot to the right. If we ever hit the edge of the hash table, we wrap around back to the beginning. And we can do this a maximum of 10 times, because size is 10. And if we get a duplicate, we should probably handle that too. So if you try inserting a duplicate, then just return. Because it's a set. So something can either be in a set or not in a set. So if you try inserting 42 twice into the same set, it'll just return. Not do anything. Yep. So there's 3 possibilities. Right? When you're inserting, is that spot open? Is it taken but with another number? Or is it taken with our number? And so we are now handling all 3 of these possibilities. It's open, it's taken with our number, and it's taken with somebody else's number. And that is a good insert function. So contains is going to be basically the same, I think. Let's copy this and paste. So if we ever hit a open slot, so like let's say we're searching now, right? So let's say we're searching for 33. So we jump immediately to slot 3. It's 33 modulus 10 is 3. The value there is 0. Nope. False. So if the spot we get to is open, we don't want to write it though. No. That's why it's nice having this little const thing here. It stops us from shooting ourselves in the foot. You see that? No, can't do it. Like, that's right. That's right, I can't do that. All right, so return false. If we get a match, then we're going to return true. And if it's somebody else, then we just move 1 to the right. And if we get through the whole thing without finding our boy, we return false. There's search. For erase, for erase, which algorithm do I want to use? I'm going to do lazy deletion. Go and do rehashing. Just not going to do erase. I'll just leave it for now. All right. So we'll just comment this one out. All right. Let's test this code. All right. 10 is in, hash catch 'em. 100's not in. 10 is in, 100's not in. Okay. So that is everything except for erase. Erase. Really, if we do lazy deletion, then we're going to need a separate array for keeping track of the status, and I kind of don't want to do that. I'm kind of lazy. Or we could just rehash everything to the right. So let's do that. Let's do a rehash. All right. Okay, so we're going to go to the slot. At worst, we're going to do order n to try and find the right place. If the spot is open, actually, yeah, if the slot's open, we just quit, right? Like if we didn't find the person we're looking for, quit. Okay. See Hazelton. If we get a match, now we got to delete. And if we didn't get either of these, we move to the right. Okay, so for this one, what we're going to do is we're going to clear the slot. So array slot equals 0. We're going to clear it. And then we are going to go to the right until we hit A0. So while array let's say slot plus 1 maybe. Go one to the right. Okay, so while array slot plus 1. I'll do this. Okay, so what we're going to do is we're going to move the slot 1 to the right. And if that's 0, we're done. If it's a blank spot, we're done. But if there's somebody there, then we are going to erase it and rehash it and then move 1 to the right. Yeah. So that guy, so int temp is equal to array slot equals 0. And then we will call insert on temp. And then we're just going to move to the next slot. So if we have a bunch of people in a row, well, I don't have my linear probing up anymore, but it'll rehash, like if we deleted the guy in slot 1, it'll delete and rehash slot 2, slot 3, slot 4, slot 5, until we get to an open spot. Yep. And that should do it. I don't know. I'm too tired to guess if this will work. Is in, is not in. Okay. Oh, I didn't order food. Here, why don't you order food? All right, so let's see. Oh, because I erased my. There's your problem right there. Not in. Boom. There we go. 10 was in before. We erased it. It's on in now. Okay. Please clap. Yeah, that's right. Not int, not an int, not an int, a t. It's gonna be a t. Thank you. Okay. Yeah. So that's a perfectly functional linear probing implementation. It's not bad. Like I said, the erase is always, like in most data structures, the erasing, the deleting is kind of the most annoying part. If I want to make this better, obviously 0 should not be used as a sign a bucket's empty. I shouldn't be stack allocating. I should be heap allocating. Just watch if I make this hash table bigger. But like, let's make it 10 million. We want hash Ketchum to be super fast. That was fine. Let's try 100 million. Let's try 1 billion. Cycle. There you go. Okay. There you go. So around, was it 10 million or so? Seg fault. You can probably zoom in on the number that it takes for it to seg fault. Seg fault. 2 mil.
It's not plasticware, it's plasticware with a question mark.
Plasticware?
You never know.
Never know.
Never know.
So yeah, somewhere around 2 million arrays, array size of 2 million. Anything bigger than that, you're thinking seg faults. So if we want to do this proper, like, which I don't know if we do. We don't really, but yeah, why not? Okay, so we'll do a R. We'll default to null pointer. And now we are going to need a... Huh? Ooh, some oatmeal. You're running off? Okay, food's on its way. So, public, I don't know what that is. Okay. So, if we want to do this more proper, like, so it doesn't seg fault on a bigger hash table, we would just do something like this, like R equals new T of size, default initialize it, and there we go. Now, do you guys remember the rule of 3? Or the rule of 5? But we haven't talked about moves yet, so we'll just talk about the rule of 3. The rule of 3 says if you got a new, then you need these 3 things. What are the 3 things we need? Good. Luke with the fast answer again. Yes. So we're going to need a destructor. So we need a destructor, and the destructor is pretty simple. Just delete the array. And then we will need a copy constructor and assignment operator. Copy constructor would be prober const prober by reference p. And we're just going to delete it because I don't want to write it. And we'll do the same thing for the assignment operator. Prober operator equals, also taking a const prober by reference p. There. So rule 3 satisfied. All right. So the Destructicon is freeing up all of our allocated memory. That's the important thing. And then rather than allowing us to duplicate the hash table or assign one hash table to another hash table, we're just not going to allow it. Because honestly, I don't see why I would want to duplicate a hash table anyway. So I'm just disallowing it. And so if we do it now, pilot, run it, let's make it 20 million this time. Then no seg fault, right? Because now we are heap allocating, right? Heap's much bigger than the stack. So that made it a little bit more professional. Even still, you know, I don't really like the fact that I'm using a 0 to indicate a bucket's open. But like I said, the fancy that we're using right now is that we're tracking hospital admissions via social security number. You can't have a 0 social, so this is fine for what we're doing. But it is a bit of a lie that will work with any type, right? Like if we try doing this with like anything else, like let's try this with a float, right? It's not going to work. You can't do modules with a float, right? Try doing this with an int. It'll work, but it probably won't work for negative numbers. So let's try inserting negative 1,000, 10,000, something like that. Run it. I don't know. Who knows? Who knows if that'll work or not? Something. It's mad about something. Right here. All right. Yep. So, really, you know, like I said, this is kind of a it's a bit of a fancy that our code works with any type. Like it works with about. Ghost is behind me. Works with like one type. Okay. So the other way you can do a hash table is by doing a forest of trees. And so we can do, let me just copy probably a lot of this. Let's see. Shift V here. Paste. Instead of prober, we're going to be calling it touch grass. And what we're going to be doing is we're going to be making an array of trees. And so the tree class in C++, standard library, is called a set. So we're going to be making an array of not t's, we're going to be making an array of set of t's like this. And so that will be set of type t of size. Oh, yeah. I got to change all the probers to touch grass. Why are you mad at me? It seems fine. All right. CW, change word to touch grass. Touch grass, like that. There we go. I was paying attention to the code. I wasn't paying attention to the name. Touch grass, touch grass, touch grass, touch grass. And there we go. No errors. Now, instead of using this linear probing thing, it's actually quite easy, right? So writing a hash table that's a forest of trees is extremely easy. All you have to do is find what slot the thing's going to go into. So if you're inserting 72, that's 72 modulus 10 is bucket 2. And then you just call insert on the tree there. So you go to array, square bracket, 2 or whatever, dot insert x. That's it. To do a contains, you just go to bucket 2 and you say if array square bracket slot bucket 2 or whichever one you got, dot contains x. Actually, no, I don't do that. Just return. 2 lines of code there, 2 lines of code there, and guess what? Erase is also going to be 2 lines of code as well. So it'll be array square bracket slot dot erase. And there we go. You can actually make them one-liners if you want. CW x. What do you guys think? That's actually a pretty good hash table. When the hash table's big, you're going to get order 1 performance. If it gets crowded and overloaded, it degenerates down into order log n performance, which is still not that bad. 1 line of code to insert, 1 line of code for search, 1 line of code for delete. It's not bad. It's not hard to implement. Good running time, one of the fastest things you'll ever encounter. And this will be called touch grass. Right, just like that. We run it again. Did you guys notice that pause there? Little pause. Why is there a little performance hitch there? Why is it glitching? Why did it take, 0.8 seconds? So what's the catch? I don't know. What's the catch? Why did that take so much longer to run if it's better? Why? Yeah, it's initializing. It's calling the constructor on 20 million BSTs. You don't have to do that for an integer, right? But the good news is you actually don't need anywhere near that many guys, because the worst case scenario is just order login performance. So if we compile it again and time it again, you'll see it's very fast. So that was why you saw that glitch, because we were initializing 10 million BSTs, which took a little bit more than half a second, right? So there you go. So there's insert, search, delete on 2 different versions of hash tables. That's enough for you guys to get all the quiz questions right for today. But there is one more topic I want to talk about today, and that is the Hashemapu. How many people here have seen the video, if coding was an anime? I don't know if I can play this without getting copyright struck. Are you guys familiar with this? It's not in CSI 40. Yeah, not everybody has. So I'm gonna play it again real fast. For those of you watching on YouTube, just search "If Programming Was an Anime" by Jomatek, and I will pause it. All right, and we're back. Fancy algorithm is still fancy even 1 semester later. Yeah, Floyd's tortoise in hair. Pretty cool stuff. So, Hashemapu is this unordered map in C++. All right, so let me just move all this, move main.cc to hash.cc. Please start over. I want to delete the old code in case you guys want to see it. Dude, unordered map. So a map is like a set, except you have a different key and a different value. So when you have an array, like let's say you have an array of 100. If you like C out array square bracket 7, you think of like 7 as the key, and I don't know, it's uninitialized. Let's see what we get. 0. Okay, what's the value? Let's initialize it to 0s. And 0 is the value. Does that make sense? So key is what you use to search for a value. So in a database, there's usually a primary key in every table that is used to find things very quickly in the table. And if you are ever trying to search a database and what you're searching for isn't the key, then it could go very slowly and you get DMV level speed. Or like if they have to search for you based on your address, then it ends up doing an order n search through every person in California through the incredibly slow DMV system. You get to stand there for 5 minutes while the system is just, going one at a time through every record in California until it finds your address, which is so frustrating to me as a computer science person. But if whatever they have set up as their primary key, like your social or driver's license number, something like that, if you punch that in, boom, it'll come up instantly. Now, the cool thing about a hash map is that it does not have to be an integer as the key. So you can do something like this. You can say unordered map between a string and a string, named addresses, and you can do something like this. You can say addresses Viale. So the address for Kevin Viale is 411 Street Lane. And the address for Luke Olson is 1234 Lane Boulevard. And the address for Stevie Sartorelli is 90210 Boulevard Way. Yeah. And so you can see here, we've got something that looks like an array, but normally arrays only take integers and they're contiguous. With a map, you can map between anything and anything. In this case, I'm mapping between a string and string, but it doesn't have to be that way. You could do something like months, January equals 31. If you have like an ordered map between string and int of months, then you can hold how many days are in each month. month in an associative array like that. So you can have any type mapped to any other type. And the first type is the key. The second type is the value. And so in this case, up here, we're just typing somebody's name and then getting their address of it. Now, what if we did this? What if we said, what if, so if addresses, here. So what if Kevin's address is in fact 411 Street Lane, then cout found Kevin at Street Lane. Otherwise, did not find Kevin at Street Lane. So how many people think it's going to print found Kevin at Street Lane? What are your votes? And Kevin, if that's your actual street address, I apologize. So you vote it'll find it? Okay. Stevie says yes. All right. Luke is typing something. Think so. Gunner. Yep. Found. Cool. Now, what about, what if we try finding Gunner? All right. So if address is Gunner Lamar is, let's see if Gunner Lamar is at 411 Street Lane. Yep. So found Gunner, did not find Gunner. Okay. So do you think that it's going to find Gunner Lamar at 411 Street Lane? What do you guys think? Or is the entry for Gunner Lamar blank? No. Everything's pretty straightforward so far, right? You guys are right. You know, it's not gonna find him. So we found Kevin at Street Lane. We didn't find Gunner. Everything makes sense so far, right? It's all pretty straightforward. Yeah. Do you guys agree? So while you agree on chat, let me just print out this little range-based for loop and just print everything in the unordered map here. Okay. So we'll say for. Now, the interesting thing about doing a range-based for loop with an unordered map is that it gives you both the key and the value pair. So it actually returns a pair. So it's going to return a pair of strings named P. So for every pair in addresses, let me make this const. By the way, you can't make it const reference. It's this weird thing. Don't worry about it. So for every pair in the addresses, we will see out that the key is p dot first, and the value is p dot second. Okay. So far, everything makes sense. Everything makes sense except for the fact that Gunner Lamar is in our database now. We added 3 people, right? If you go back and look at the code, we added 3 people. But there's 4 people in the database now. Gunner Lamar is in the database with his name and no street address associated with it. Looking for him created the entry. That is correct. And so this is a reason why using the square bracket operator with when you're searching for things is not recommended. Because if the person's not in there, it makes them. It'll actually insert a blank value for Gunner Lamar and put it into the hash table, which is not at all what people would expect from search, right? It is absolutely a sharp edge. It is a confusing, weird thing that you have to avoid. So if you're searching for people, what you need to do is you can use square brackets, But you can do something like this. If addresses dot contains Gunnar Lamar and that. So by putting this in first, if that's false, then it does not do this part here. So C++ and C, for that matter, have something called short circuit evaluation. So if the first clause is false, then it does not execute the code in the second clause. This code here in the second clause would actually insert Gunnar Lamar with a blank address into the addresses database. So by putting this in here first, we can first sort of vet that Gunnar is in the system to begin with, and if he's not, then it doesn't create him. Because if that's false, then it just skips everything else. So we do this, then you'll see that we do not find Gunnar, and you can see that he is now not spuriously being added to the database. Another way you can do this is you can do .at addresses .at Kevin Dugale, like that. And then if Kevin is not in the system, then it doesn't create him. Let me make another example of this. Okay, so if we check for somebody who's not in there, so if we check for, I don't know, who wants to not exist? who wants to be searched for and cause the code to crash? Because remember with @ if you go out of bounds in a vector, right, with .at, if you go out of bounds with .at in a vector, it throws an exception. In an associative array, which is what this is, if you search for somebody with .at and they don't exist, it throws an exception, kills your program. So you want to search for Bob? Anyone else? Any student want to be responsible for the death of a program? Or do you just want to go with Bob? Brandis. Okay. Noah Brandis. All right. So we search for Noah Brandis, and if Noah Brandis's address is 411 Street Lane, we'll print what? Whatever, but he's not in there, so watch what happens. Segfault. Not a segfault. It's actually a good crash. So it throws an exception. We didn't catch it. Terminates unordered map, ::@ killed our program. All right. Cool. Nice. Better way of doing it would just be to, again, use .contains first. So use .contains, see if they're in there. If they're in there, then you pull their data using square bracket or .at. Either way is going to be exactly the same, because if they're in the database, then addresses square bracket and addresses .at is it's going to give you the same performance, the same thing, the same behavior. It's only when something's not in there that they do something different. If you try searching for Gunnar's address and he's not in the system, it adds him to the system. If you search for Noah's address and he's not in the system, then it kills your program, which is actually better in a lot of cases. So, yeah, again, to fix that, you could simply say if addresses contains Brandis and addresses.at, like that, and then everything will be fine. Everything's fine, no crash. And so a very common thing is, like, if you're doing a database, then you have something like class person, let's make it a struct, whatever, struct person, and they got like a string name, address, whatever, and then you can make in like a social or something like that, and so you could do like an unordered map between like their social and like the person, right? And then you can like db.insert Bill Kearney, my address is of course 111 Main Street. So inserts another, you don't like it? Okay, well, whatever. We'll just do this. Scrub back to Bill Kearney. Equals that. That works. DB, sorry, it's got to be an integer. Right. Right. social. Let's do this. DB. Social security number of 1234 121234. That's too many. 123 121234. Social security number of that is equal to a person is a name and address. So Bill Kearney, 101 Main Street. Okay. Street. And so you can use the social as the key, and then read and write data of the entire record for the person. You can have name, address, income, age, date of birth is probably better. Gender, all that kind of stuff can be in the person record, and you can sit there and read records and write records using the social as the key, and it will find it like that. And so that is what your next homework assignment is going to be. So your next homework assignment is called Gilded Rose. It's based on a famous CodeCod exercise for refactoring bad code. I'm not actually going to give you bad code. I'm actually going to give you perfectly fine code. And what you need to do is write a inventory program for a fantasy magic item shop. So if any of you guys have ever played World of Warcraft, there is an item called Sulfurous, that Hammer of Ragnaros or something like that. And so you can have that up for sale. CD Gilded Rose reference. So you can have that up for sale. So here's a list of items that are for sale, like maybe in our magic item shop. So the first item here is an iron helmet. It's worth 10 gold pieces. It expires in 1,000 days. The 1,000 days is like the sell by date. You start off on day 1. And inside of your magic item shop simulator, people can buy items, you can stock new items, and you can advance time. Yeah. And so on day 1,000, the iron helmet starts rusting. So up until then, it's got a value of 10. After day 1,000, the value drops by 1 gold piece every day. So it goes from 10 gold pieces to 9 to 8 to 7. Once the value hits 0, it's deleted from the system. Sulfurous is a legendary item. So you can see that there's a option here for special attributes and things like that. An iron helmet's boring, it's got nothing. Sulfurous is a legendary item. The only thing that makes legendary items interesting is that they can exceed 100 gold pieces. By default, items go from 1 to 100 gold pieces in value. A legendary can be more than 100 if you want. It expires in 7 days. So on day 8, it drops to 221. On day 9, 220, etc. You've got your Chateau Latour, which is a wine. And so it's aging. Aging items go up in value every day. So every day that goes on, it goes 47 gold pieces, 48, 49, 50, up to a maximum of plus 100. So a 1900 Chateau Latour would be worth 147 gold pieces, right? It's been over 100 years in that case. Yep. Tool concerts. So limited time items gain value the closer it gets to the expiration date. So it goes up a value of 2 every day towards the expiration date. So it'll go 90 gold pieces, 92, 94, 96, 98, 100, all the way up to day 10. But the day after day 10, they drop to 0 and are deleted. Because nobody wants to buy tickets to a concert that was yesterday, unless you're like apparently a Swiftie wanting to pretend to have some street cred for seeing a, Eras Tour concert that you didn't, actually go to. It's all about the auction house, yeah. And then we got conjured items. So conjured items lose 2 gold pieces per day after their expiration date. So conjured water, starting on day 3, the conjured water will go from 20 to 18, 16, 14, 12, 10, etc., etc. So conjured items expire much more quickly than regular items. So what you're going to do is you're going to have an item class. The item class is going to be in items.h, like this. And you're going to have the name, the price, expiration date, special attribute in it. You're going to make good class design. You have to have a constructor. You're going to have a double left arrow operator, a double right arrow operator to do cin and cout into the object. You don't have to put it into an items.cc and an items.h. You can if you want, in which case you have to make a makefile for it. Or you just do everything in items.h. It's fine too. You're not allowed to use using namespace std in a header file. That's just good practice you should get into, because then anybody who uses your header file, you've decided for them that they're going to be using namespace standard as well, and people get miffed at that. Because there's a lot of people that just love STDs. Just love STD. Like, they just can't get enough of typing STD over and over and over again. It just makes them so happy to just roll around in those STDs. So if you make that decision if you make the decision they shouldn't have STDs, they get mad. They're like, no, I want to have STDs. So you can do something like this, where you can like use a specific thing, and then you can just type string like that. Using is pretty cool. You can also create type aliases and things like that. So you can say like using i32 equals int, like that. And then instead of an int, you can type i32, like that. You do that. It's fine. If you want to make your code look like Rust, it's fine. It's called type aliases. I typically do them anytime there's like a super long like class name. So I'll have like using GC equals like chrono : hi. They have these like super dumb long names, and so I use using to shorten them because they're stupid. But yeah, you can't use using namespace std in the header file. In your implementation file, the .cc file, main.cc, knock yourself out. It's fine. But for this, I'm going to try and teach you guys a little bit of proper coding style, which is using namespace std is fine in an implementation file, a .cc file, but in a header file, you should really try to not do it, especially if that header file is going to be shared with other people. So your lab time for today, lab time begins now. I want you to get item done. So there are 4 things you need to keep track of on an item: name, price, expiration date, and a string containing the special attribute. You'll need the constructors, and then you will need a double left arrow operator to print it to the screen, and a double right arrow operator to read it from either a keyboard or from a file. Once you got that, screenshot it, send it to me on Canvas, and you'll get your 10 points for lab time. This assignment will be due next Friday. So I'm giving you guys 9 days on it, not because you need 9 days, but because we're going to the Computer History Museum on Saturday. So giving you guys kind of like an extra 2 days to, make up for the lack of a day on the weekend. Any questions about it? Hype for the museum trip. It's going to be fun. It's a great place to go to. We have been trying to return to the Computer History Museum for years now. We went back in like 2016 or 2017, something like that. We've been trying to return since then, and the trip has been canceled over and over and over again. It's so bad that actually on Sunday they mailed me and they're like, "Are you guys actually coming this time?" And it's just like we've undoubtedly got such a reputation for canceling on them. They were just waiting for us to be like, "Yeah, we're not coming." So I don't care if the bus breaks down. I'm walking. I will take an Uber to Mountain View. I don't even care anymore. We are going on Saturday, 6:30 in the morning, at the flagpole. So it's a cool place. It is a really cool place, and I'm hyped for it too. So that's it for today, guys. Hash tables, very useful stuff. Like I said, my favorite data structure. You should probably use the hash table for this assignment, or your code is gonna be too slow. Because look at this, there's 100,000 items. Some of these input files are like, they're pretty big. Yeah, some of these things are pretty big. These test cases have a lot of inserts and deletes in them. If you try using any data structure other than a hash table, you are going to time out. Okay, so make an item class, make a Hashimapu, All the items will be searched for based on their name, you know, so you don't have to do anything crazy. And yeah, so have fun with it. That's it for today, guys. I will see you on Friday. Peace.